Today we will study about the practical signal. In this class we are focused on the audio signal and the image signal. Firstly, the audio signal seems like a one-dimensional one, like that one. At this moment I extracted the left sound only. Okay, to understand the audio signal I would like to give examples from here. This code shows that how to check the audio device attached to this computer. So I run this one and create an audio object from here. And if I check up the default audio, at this moment I have a default device. Here shows that the default setting. The default setting is this one, that the sound is sent to my monitor, and the output channel is 2, and sampling rate is 44K. This is the standard for the CD. 48K is a DVD-ROM standard. And I would like to check the input device. This shows the input device. The default is USB or mic is the default, and this is single channel. Dual channel means that the left and right sound, but in microphone cases there is a single channel. It doesn't have left and right stereo sound. This is stereo sound, but this one is mono one, and the sampling rate is the same as 44.1 as our device. But this is the default device, but I have my computer has more devices attached. I can check it that right from here, that if I run this one, then this shows that the other devices that can be available, and also you can check up the whole device attached in this computer. So you can select one of them. At this moment I'm using this one, the micro 4. This is default. I set it up, and this is the output speaker. So that's the default setting. I said that this was the default setting, but my computer has a lot of resources that can be used as the audio device. This one is related to the hardware, so I would like to clear that object. So this is the environment to handle the audio device. And the next one is to read in the audio sound. So here is a audio sound reading. At this moment I read that the piano sound. I would like to show you that the sound device is this one. Okay. This sound is reading from here, and I check up that the state of that one. It is a 44.1K, and number of frame is this much. And as you know that this one is a CD-ROM standard, and I can scaling this data is reading, and after scaling it, and the left and right sound are separated at here. So the reading data size can be checked here. Okay. There is a 2 channel, left and right channel, and this is number of frame. I separated the left and right from here. That this one is left sound, this one is right side sound. I can plot that one from here. That this one is a plot left signal, and this is right signal. That is plotted over here, so I can plot that one over here. Then this is the sound data. As we heard that that's the piano sound. The left signal looks like this one, right signal looks like this one. After check it that I import the CSV, and I can write data. I only some segment of the left signal is scaled up by the 16-bit. It's a 1 byte data, So I changed it. It's a 16 integer, and that's it. That is here. That is written as a CSV. So this is the audio signal that I would like to write down. Then I can write data by learning this one. Then I can check up this file. Okay. Okay, the files are given here. This is the audio sound for this is very wrong data lines. Only left sound are stored here. If I would like to change the shape from low data, then I can reshape that one. Okay, then this is single line that I can rewrite this one. Okay, run this one again. Then it shows another file. It maybe looks like in a vertical way. I changed the shapes of that one. This is the audio signal that we check that one. What about the image signal? Here shows that the image signal of 28 by 28 digit. You can see this is a 5. 0 means low intensity, so this is a black one. This one number scaled up to 255, 0 to 255 scale. You can see this is a 5. This is the y-axis and x-axis. This shows that the image data. From here, that I can read in the image data from here. MNIST data can be downloaded here. That is this file. From this file, I read in the image data. So that's this image. Basically, this image is a binary data. So I need to convert that one into NumPy array. And among the NumPy array data, I selected, you know that the MNIST gives 60,000 samples, handwritten digit sample. Among them, I would like to select just one of them. So I choose that one. Okay, I would like to reshape that one into 20 by 28. Then okay, this shows that the 28 by 28 and the 60,000 samples. So among them, I can I select one of them. 0, the first data. Then you can see this kind of data. This is actually the okay, this one is actually this data. So you have some idea what is the audio signal and what is the image signals. To understand the signal processing, I would like to explain about filtering, or the other name is convolution. So to understand the 1D convolution, I'd like to give an example from here that okay. Firstly, I would like to generate input XS and impulse response HS. You may know that the signal can be processed by system. This one is X. S is the input, H S is the system, and the output is convolution between them. HS convolution, XS is the output. Okay. To evaluate that one, we can take the convolution. Okay, this is the input. So this one is XS, HS. So this is the impulse response. This one is input. We can evaluate the convolution from here. We have 3 different modes. The first one is a full mode, same mode, and valid mode. So you can compare between those the convolutions. Okay, evaluate this one. So we evaluate one. This is the full mode. This is the same, and this one shows that the valid one. You can see that the valid is included all the other convolutions. This is included here. You can see that the full mode is symmetric. This is valid one padded left and right hand side symmetrically, but in case of same, it is unsymmetric. It depends on the data size, between the data size of input and the impulse response. But usually the full mode is symmetric, but the same is not. But valid is included old mode. And the another one is, we know that by taking the Fourier transform, this is XS j omega, and impulse response becomes the HS. Then Y, Fourier transform of the output signal, it can be expressed by HS dot product XS. Just the product in the Fourier transform gives the output. We can take the inverse Fourier transform to get the Y. So that operation can be shown here, that we would like to check the firstly the check up the length, and adding the short one need to padding the 0 left or right hand side, and from here that the HS and XS are this one, but pad XS is the same as XS, but the pad HS looks like this one. 0 is added to become the same size, and then we take the Fourier transform of padded one and XS and HS, and we take the product between them. Then we get the YS. That's the Fourier transform of this one. And then we can take the inverse Fourier transform. That will give the convolution value. So this is Y4. So you can see that the same valid data are included here. But the first element is not equal to same. So it means that it is not like same. You need to understand this one is a cyclic padding. This is not zero padding. In this full and the same mode, we padding the 0, but in this case, you need to the cyclic padding should be done. Cyclic padding can be done from here, that the wrap around pad is this one. So XPS is a cycle padded. You know that this is the original data, as we know that XS is 1 through 4, but 4 is the last digit. That is a prepended at here. That is a cyclic prepend. So if you after prepending, you can take the convolution by valid. That is this one. That corresponds to the Y4. Y5 is this one. So you can compare those things by use of this one. So what is difference? The full convolution is this one, same, and this one is valid, and FFT is this one. Cyclic padding, you get the same result of the FFT convolution. So this is the convolution, the taking in the full mode, same mode, valid, and sometimes we need to take the Fourier transform, this operation. All those things are not equal. To understand that one, I would like to give you some Excel example. From here that I generated the HS and the YXS. From here that this one is XS, this is the input, and this is the impulse response. Then the full mode convolution is just the product of 2 and 1 and 1 and 0. This is zero padding effect actually. That is calculated in these directions. Then this number gives the full mode. This one is equals to this full mode convolution. Okay, this is full mode convolution. And the same is this one. You can see that the same is this one. This is the same, but the last digit, this is the end of them. But you can see the end is like this one. You know that 2 is, you can see that the 1 is multiplied 4, 2 is multiplied 0. So 0 parity at the right end. So this is 1 times 4, 2 times 0. That's why it is 4. But in the valid case, we only calculate up to here. That this is the 4. This is 6. So you can see that okay. So it's 3. You can see this one is a product T multiplied by 2. This is 8 and 1 3. So 2 4 8 1 3 is a 3. So that's why it is 11. That's the same operation. You need to understand that the convolution, just the flipping to 1 sequence is 2 1 like that, and multiplied. That will give this result. So this is the same operation, but we need to stop it here. You know that it's the same as a full, but this is dropped out. That's the same mode. Then the number of data is the same as the input. And the valid case, data should be overlapped each one. You can see here that the 2 is 4, 1 is 1, so 4 plus 1 is 5. That's this one. And this is the last one is the same way. This one is a 2 4 1 3, so that is 11. That's the valid one. What about the FFT Fourier transform spectrum? To get the Fourier transform, we need to zero pad at HS. It's because it's a short sequence. And after that, from here, that you can see data analysis. From here, you can take the Fourier transform. The Fourier analysis is shown here. To activate that one, you need to add from the additional function, and you can see that the analysis tool should be added. Then you can see this the tabs and select the Fourier transform, and the sequence to take the Fourier transform at this moment XS is this one. After Fourier transform, I would like to save the data on here, okay, and take the Fourier transform. Then it will give Fourier transform of this one. And similarly, you can create Fourier transform of this one. Fourier transform is taken, and the Fourier transform target sequence is this one. After Fourier transform, I would like to store at here and learn. Then I get the Fourier transform of that one, and y can be evaluated by the product between them, so I can evaluate that one. After that, I need to take the inverse Fourier transform of this one to get the time series. By product of these XS and HS gives a large capital YS, the Fourier transform. Inverse Fourier transform can be evaluated from here. Here is data analysis, and I select the Fourier analysis, and the input range is this one, and the output range are given here. Okay, so I would like to clear it first. Okay, let me clear this one before calculate. So Fourier analysis, select input sequence and output range from here. 14, okay, and you need to select this inverse Fourier transform. Basically this is a Fourier transform, but if you select this one, inverse Fourier transform are performed. So this is the result of the inverse Fourier transform. You can see this one is equals to this one, okay. So this sequence 6, 5, 8, 11 is 6, 5, 8, 11, this one. So I hope that you have some idea for the convolution. The same thing can be done in case of impulse responses are a little larger. Then you can evaluate the full mode convolution and the same mode convolution. Same mode cases, the input sequence size is the same as output, and the valid case is this one. So you know that 3 to 1, 3, you know that 3, 3, 2, 2, 1, 1. So that's why it's a 9, 4, 1. That's the 14. Is this terms 9, 4, 1. Okay, that's a 14. The another one is that this is a 3, 2, 1. 3 is a 12, 6, 2. 12, 6, 2. 12, 6, 2. That's 20. Okay. So this is the valid. The same thing can be done by use of a Fourier transform. A little larger can also evaluate it. This is the input sequence. This is the impulse response. The same way, the full mode can be evaluated in this way, and this can be repeated here. And the valid, you can see it's the same from here to here. You drop out here, and also you need to drop. That becomes the same. The valid is this one, the fully overlapped one version. And when you would like to use the Fourier transform, in that case, you need to zero pairs as required. In this case, zero pairs are done in this way. This one is zero paired, and take the Fourier transform of that one that is given here, and the HS Fourier transform is performed from here, and just the product between the HS and XS, that gives this one. Lastly, we can take the inverse Fourier transform of that one. That is this result. That is shown here, that the 7, 60, 50, 40, 30 is the valid data. And the another data is not equal to here, that the full, same, or valid, all of them is zero padding. But this one is a cyclic padding, like this way. This is the cyclic padding. Original sequence is this one. You know that the last sequence is the cyclic padded like this way. This is repeated. If you study the Fourier transform, the discrete Fourier transform, you may understand this repeated property. Okay, I hope that you have some idea how to take the convolution in the 1D case. What about 2D? 2D convolution can be performed in the image data. Okay, I would like to give an example. So this one is the image data. You can see this is number 5. The 0 is a black one, but if a higher number shows that the brightness is a white one. So this shows that the number 5. In the image data, you can store the image into a CSV. Okay, this one is a CSV file, or you can save that one into PNG data. I stored that one CSV data and PNG data. CSV data is this one. Its number stored from into a digit like this one. I opened this one. That's actually this one, and the same digit also stored as a PNG data, as a image data. So this is this image data is okay, this one. This one is actually this number. Okay. So how to take the convolution between them? So this is the kernel. I need to divide by 9. You know that 1, 2, you get 3 by 3. It's the total sum is 9. You can see this is 9. So after taking the convolution, you need to divide by 9. The convolution can be done by this sliding. You can see this one is the first sliding. Okay, you need to convolution. You need to evaluate by product this one and product like this one. The next we product the sliding to the right hand side, and you can product this one like this way. You can evaluate in that sequence in the right hand side. In the bottom side, this one can be moving like this way, this one and this one like that. The center data can be obtained like this way. So after convolution, you know that this one is a 3 by 3 image, this one is a 22 by 22. After the convolution, it will give two increased in the low and the bottom, and it will be 2 to 4 will be increased. So that's a 26 by 26 number can be obtained from here. That this one is 26. Okay, this is 26 by 26. Data can be obtained. How are we going to evaluate that one? You can see here that this one is array. This is constant number. The dollar sign means a constant. This 9, 1 digit is multiplied to this array, and then you can slide the 1 in the old image. You can see you can sliding the old way, or you can copy that one. You can copy and paste the old function. Then that is evaluated like this way. This is the image convolution. You know that this shows that the basic idea. This is kernel, and I said that the array product is performed and divide by 9 because the kernels should be normalized by 9 to get the normal energy. If you didn't divide by 9, the strength is increased 9 times higher. So you need to divide and take the integer part. So that is the operation. You can see here that in this case, this kernel is a product of this one, and it's the same. This one is a product between here, and what about this one? That is a product between this one and this kernel. So this is the image processing. I hope that you get some idea how to take the convolution in 2D image cases. Now I would like to give some example. The first example is a sharpening. Sharpening can be done by taking out some blurred part of the image is removed from the original. I mean that here is the original image are given, and we take some blurring by use of this kernel. Then the original image are blurred like this one, some blurred one. By subtracting these to 1, it means that the smoothed one or blurred one is subtracted from the original image. That is a detail. So this is called the detail image. You can see that the image convolution can be done like this one. This one is a kernel, and this is the image. By taking the convolution, you get the output image. The original data is convoluted by this kernel. Then you can get the blurred one. By taking the subtraction between these images, you can get the detailed image. After you get the detailed image, you can add up the detail to the original data by scaling alpha. Then this one is added to the original one to sharpening. You can see that it is much clearer image can be obtained. Compared to the original one, you can see a little stronger, and the sharpening image can be obtained. How are we going to do that? Let me show you that process. Okay. First, I need to import required package. And matplotlib to plotting the data, and to handle the image. Matplotlib image tool package reading. And to take in the 2D convolution, I would like to import SciPy signal package. So I think that will be enough. So this is run. Okay, I read in the old package. And first, I would like to read in the original image. Lena.png. Okay, I would like to read in that one. So image org.shape. So 512 by 512 image are reading, and I would like to plot the image in by comparing the each data to generate a kernel. Before that, I would like to plot that one first. Figure 1 is define the plot. Figure size 21 by 7. I would like to overplot 3 different images. So I would like to generate the figure 1, and the plot is grayscale. And first image can be plotted at here. 1 by 3 column. The first image is this one, and show image. Right. So this will be shown over here. Figure 1 will be drawn like this way. Then we can see that image. You can see here that that image, this one is the original one. And next, I would like to get the blooded image. To get this one, I need to create this kernel. To get the kernel, HS should be generated. mp.ones 5 by 5 and normalized by 25. This will generate the HS kernel. That's this one. This kernel shows that this one. After generate, I would like to get the blooded one. Okay, image filtered. One can be obtained by taking the convolution. To get the two-dimensional convolution, I would like to use this package, convolve 2D. Image org and HS, and mode I would like to take the same. So by taking this convolution SGN, sorry. Okay, SGN. Okay, I need to take the convolution. I get the filtered image from here, and then I can plot that one. That generate another canvas. Fig1 dot add subplot 1 by 3, and the second canvas I would like to use that I'm show at this moment image filtered 1. Okay, this is not taking quotation. And after that, Fig1 dot canvas dot draw. Then I can see another figure. Okay, let's see here. You can see that this one is a blooded one. That's a filtered one, this one. So after taking the filter, you can see there is some smoothed version. Okay, after filtering, you get this one. The last, I need to subtract this part from here. The subtraction can be done to get the detailed image. Image detail is image org minus image filtered 1. So this gives the detailed image. After get the detailed image, I would like to plot that one also. One by 3, and the third graph, this canvas, will use to display the detailed image. Image detail will be plotted over here, and then I can see the image from here. Okay, this is it. Okay, up to here. So this is the original, and get the filtered one by use of this 5x5 kernel and smoothed one, and by subtracting I get the detailed image. This detailed image I used to sharpening the original, improve the aspect, the clearness of the image. So this is the first processing, and next I would like to make it sharpening. To adding up, you can see here that the original image are superimposed by detailed image by this portion. You can choose the proper alpha value. At this moment, I would like to choose 20%. So this is the 20% alpha used, and the image sharpened will be image org plus alpha times image detail. Okay, so I get the sharpened image, and to display that one, I need to create another figure. At this moment, I need to the same figure 21 7, this one, and AX0 AX3 4, this is 4, is figure 2 dot add 1 by 3, and the first one, and AX5 is a figure 2 dot add subplot 1 by 3, and the second figure AX6 figure 2 dot add subplot 1 by 3, and the third one AX4. I would like to show you the original image, and next canvas I would like to show you that the image, the detail, and the last one sharpened one, and figure 2 will show up here. Okay, then I can do that job by running this part. So I have the process here. This is the original, and by adding the detailed image, we can sharpening the much clearer image can be obtained by these techniques. This one shows that the basic operation, but if we have a better kernel, like compared to this one, then we have a much better image can be obtained. Among them, the Gaussian filter, Gaussian kernel can be used. Gaussian kernel is defined by these equations. Okay, the one-dimensional cases we are using this one, but in the two-dimensional we can using this one. We can take any size of the kernel. I would like to show you how to create the kernel. I would like to take the sigma value around 5, and that's the sigma. And to get the two-dimensional Gaussian, and I need to create a mesh grid, x-axis and y-axis. The mesh grid can be generated by this function, and we need to providing the x-axis and y-axis. So x-axis, I would like to starting minus 10 to the 10 step by 1, and that is the first x-axis the range, and the y range also arranged minus 10 to the 10 by 1. Then I can generate the mesh grid data x and y. So I run this one. Then x dot shape, this is 20 by 20 minus 10 to the 10. Y dot shape, this is also has the same shapes. And to get the Gaussian kernel, K-Gauss. I can use this equation. I would like to evaluate the exponential function first and then divide this one. And p dot exponential and minus x square plus y square divided by 2 divided by sigma square. So this shows that this part, the exponential minus x square plus y square divided by 2 sigma square, and divide by 2 divided by pi divided by sigma square. So this is it. This is the kernel. So we get the Gaussian kernel. We can see the shapes of the Gaussian kernel. I would like to draw the Gaussian kernel. In case of the 5 by 5 kernel, it's a uniform. As you can see here, that it's a uniform kernel. But in case of Gaussian, it is non-uniform. So I would like to plot that one. Another canvas will be generated. At this moment, I would like to use a single figure. Okay, and 7 is a figure 3 dot. And 1 by 1 and the first one. Okay, image show and Gauss. Then figure 3 that show will draw this one. Okay, I would like to run this one. Then this is the Gaussian kernel. It is non-uniform. You can see that the center is bright, is a strong weight. The outside is dim. That means that the weighting factor is lower. By use of this one, we can create another smoothed one and get detail. That will be better performance compared to uniform kernel. So the other operation is almost the same. By use of this kernel, we can do the same jobs as we have done in the filtering, and then get the detail image and the sharpening. That process can be done by use of that one. And the last one is as we talk about that. Okay, we need to close that this image. So this one shows. Okay, I would like to run this one. This is the original image, and in somehow the hand motion is the shaken image can be obtained from here. If we have a shaken information, then we can deconvolution. By taking the convolution of this one, we can get the recovered image. So the original image is shaken by the hand motion, and then this one is the shaken image. It's not that clear, but if we have how the image are shaken, that information is deconvoluted. Deconvolution is applied to this image, then we can get the original image can be recovered by that way. All these things are using the convolution. Convolution can be evaluated in the space or time domain, as we heard that one. But the same thing can be done in the spectral domain. Spectral domain convolution is quite efficient because of the Fourier transform algorithm is very nice. And by use of this Fourier transform and inverse Fourier transform, we can evaluate the convolution indirectly. The direct calculation is the time-consuming, but the indirect method is quite efficient the evaluation process. So this is the one of the practical application for the convolution and the Fourier transform.